This is an RNZ podcast.
They say life is stranger than fiction.
Could we do that on Middle-earth? Well, there's no evidence of electricity anywhere on Middle-earth.
No.
But on the other hand, we're in the Mines of Moria here, right? We're right down in the deep depths of the earth. Who knows what's going on down there?
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
So we could perhaps have a luminescent material. We put enough into our inlay that when it's dark, we can see the luminescence from this blue light, but when it's light, we can't actually see it.
Hi, I'm Bryan and you're listening to Sci-Fi Sci-Fact, a podcast where MacDiarmid Institute scientists fact-check popular science fiction. In this episode, Dr. Chris Bumby, MacDiarmid Institute Associate Investigator and Senior Scientist at the Robinson Research Institute of Victoria University of Wellington, delves deep into the Mines of Moria and brings us the science of Mithril from the Lord of the Rings.
Here's a pretty thing. Mithril. As light as a feather and as hard as dragon scales. Let me see you put it on. Come on.
Now this is I'm assuming it's a metal. It's both extremely strong but also light and other things. But you can sum it up better than me, I'm hoping.
Well, maybe. I have to admit, I had to go and do a brief bit of research myself because I'm a scientist, not a Tolkien literature expert. But I think maybe the best place to start is to a quote from the books, in which Gandalf talks about this material Mithril while they're walking through the Mines of Moria. And he says, "Mithril, all folk desired it. It could be beaten like copper and polished like glass, and the dwarves could make of it a metal, light and yet harder than tempered steel. Its beauty was like to that of common silver, but the beauty of Mithril did not tarnish or grow dim." So hiding in there, I think, is quite a lot of facts about what this material is. It seems to be a precious silvery type metal, but very lightweight and immensely strong. And they used it to make armour. So the big plot device that turns up several times, both in The Hobbit and then in The Lord of the Rings, is this chainmail coat of Mithril that is passed from Bilbo to Frodo.
Yeah.
And at some point saves Frodo's life.
Yeah, that's right. Yeah, spear right for his heart or something like that.
That's right.
It just bounces off or something like that.
That's right.
Just knocks him over. Did Tolkien, based on that, know his periodic table?
It's a good question. He wrote these books back in the late 20s and 30s. So at that point, there were still a few elements in the table, actually, that hadn't even been fully discovered or at least isolated as a pure element. But he's talking about a material that is that probably
material
possible?
Yes, that's the question. Is it feasible? And if it is feasible, what are the candidates in terms of the metallic elements?
Well, so I think the way to think about this is a bit more in terms of a materials design problem. So when we think about doing materials design, the first thing we need to do is to define our problem properly and to specify what we need from our material.
Materials design.
That's right. So if
making a material that's then used to make other stuff.
Sometimes just choosing a material.
Mm-hmm.
But either way, we need to have a list of properties that we can go to and we can say, these are the things we need our material to do. And then we go to our toolbox and we say, well, what materials have we got out there that can do that? So the first thing I think we need to do is go back to that quote I started with from Gandalf and just isolate what it is we know about this material and what makes it different and special. And those are the things that we actually need to find a material that can do that. So first off, we're told that it's this lightweight, strong metal. And we're told actually that it can be beaten into shape, which as a materials scientist we understand in terms of a property called ductility and malleability. So this means that we can bend it and it doesn't break, but it takes on the new shape that we've bent it into.
If we mixed iron with carbon, we could have steel.
We could.
But this isn't steel because steel's quite heavy, isn't it?
Well, I think, to be honest, that's exactly the right place to start, because Tolkien and the world of these books is based very much on medieval technology. And in that concept, steel has been around for a very long time. The Iron Age started 2,500 years ago now, and steel was been the key metal through much of human history up until really the last 100 years or so. So when people think about metal, they often immediately go to iron and steel, and we know the density of iron and steel. So if we're talking about something that's lightweight, I think a good comparator to put in here is to say we need something that's a lot lighter than steel. And it needs to be beaten into shape. We need to be able to make it hard, right? So we're making an armour out of this. So if we whack it with a big sword, we don't want to be able to cut through it. It needs to be hard. And we're also told that it's rare. It doesn't actually turn out very much. It's rare in occurrence. Now, we're in Middle-earth. I don't know a lot about the geology of Middle-earth. We can probably make some outlandish claims.
There are mountains in it, lots of mountains.
There is, and dragons
Mineral
living
deposits.
under the ground and all sorts of things. So who knows?
And terrible demons as well.
That's right. I think we'll come back to that in a minute. And just to finish that list of properties, of course, we're also told that it's shiny silver and it doesn't tarnish or corrode, so it doesn't rust or form any other sort of discoloration over time. So you asked, can this property exist? Well, I think we have to take it as read that it is a metal. Tolkien's not a material scientist. Maybe he was wrong. But the moment we talk about something that is ductile, that we can bend and stretch into place, and importantly, something that's shiny and silver, that's almost always a metal. And that's because metals are defined by the fact that they have a series of atoms that are usually in a crystal lattice, and they have electrons that move about between these atoms. And because they all move about, when light shines on the surface of your metal, it is immediately reflected straight back. All these little electrons jiggle about when your wave from your light, which is actually just an electric field going backwards and forwards, your electrons jiggle back about and they just reflect the light straight back at you. And that gives you a shiny silver material.
So that is why metals are shiny.
That is why metals are shiny. It's why nearly all metals in the periodic table are silver. There are a couple of notable exceptions, which you can probably think about if you think.
Silver's not one of them, by the way, is it?
No, silver's not one of them. But if you think about in modern life, then the wiring in our house, okay, is copper. Copper is not silver. Copper is a sort of orangey colour. And the other coloured metal that we come across a lot, of course, is in jewellery, in gold, which is also not silver. And so those two metals are a little bit weird. And what happens in those metals is that there's the electrons in the metal actually go through a resonance in the optical spectrum, which means that they absorb a little bit of light somewhere in the region where we can see it. And so that just pushes the colour it reflects back to one side of what we can see with our eyes.
So it's definitely not going to be gold or copper.
No.
And it's probably not iron because iron's too heavy. What are we left with?
I think we are left with, looking through, magnesium, aluminium and titanium. Now, interestingly, these are all elements that are used quite a lot today in aerospace alloys and in quite a bit in the vehicle, lightweight vehicles and other aspects as well. But of these three, I think we can also knock out magnesium for much the same reason as we knocked out lithium and sodium.
Isn't it?
It's fairly reactive. Yeah. It doesn't actually catch fire if it gets wet, but it does corrode pretty quickly. And particularly if you've got any salt water near it, it doesn't last long. So I think that leaves us basically with aluminium and titanium.
Now, were they being smelted back in Tolkien's day? Aluminium, that sort of really mass aluminium production relies on electricity, doesn't it?
It does. Now, the aluminium smelting process was discovered in the late 1880s. It was actually one of the very first industrial processes that made use of electricity. It predated some of the work that was done actually in terms of large-scale electricity generation. So the early experiments were done using big zinc pile batteries, and a large portion of the entire experiment that Charles Hall did to discover this was putting together this massive battery so that he could actually run his cell.
Wow, that sounds like a story in its own right.
It is. But that's too long for here, I think. But anyway, the whole Hero process is how we make aluminium today, and that is an electrolytic process. Could we do that on Middle-earth? Well, there's no evidence of electricity anywhere on Middle-earth.
No.
But on the other hand...
There's magic, but there's not electricity.
No, there isn't. But on the other hand, we're in the Mines of Moria here, right? We're right down in the deep depths of the earth. Who knows what's going on down there? So you could possibly consider some quite complex system which uses maybe a hydro wheel to generate and move some magnetite round, past some coils of metal and make enough current to get moving. They certainly got the temperature. We know that when we saw the forges of Saruman in the films, we saw hot metals being forged there. So aluminium doesn't require that higher temperatures. Aluminium melts at a temperature just above 600 degrees centigrade, which compared to steel, which melts at 1,500 degrees centigrade, is actually quite low.
And aluminium there's a film that forms an oxide that would stop the corrosion thing.
There is, absolutely.
But is aluminium that tough really on its own?
So, this is the tricky bit, right? So far we've just talked about elements. And titanium is the other element that we've talked about here, and maybe before we go on too further, we should also note that if aluminium's difficult to make, titanium is really difficult to make. It's a very complicated industrial process that requires us to, first of all, react the material with acids and then to go through a complex industrial distillation process and then react it with another metal that we've made via another electrolytic process. So I think that's too complicated for Middle-earth.
It's the kind of stuff dwarves might get into, though.
Well, maybe, but that requires an awful lot of accidental discoveries without all the other industrial developments around.
So you reckon the aluminium is a candidate, but maybe it's not the whole story?
I think it can't be the whole story. For the reasons you've just talked about. Aluminium is actually quite soft if you've got pure aluminium. And the other issue you have with aluminium is that it undergoes what's known fatigue failure. So this means that if you take a bar of aluminium and you start bending it backwards and forwards, and maybe people have done this, and you can bend it back and forwards a few times, it starts to get quite hot. It also starts to get quite stiff. And after you've done that maybe 8 or 9 times, you'll find that it can break. And that's because as you've worked that area in the middle there, the grains of metal have become progressively weakened, and eventually they break and fail. So that's a bit of a problem if you're looking for a type of material that you can use and wear and lean on and bend and do all those things you do in armour or any other significant artefact. However, one of the great things about metals is that we aren't just limited to the elements. We can actually start mixing them together. In the aerospace industry, there's a lot of magnesium aluminium alloys made. But if we want to look at the winner in terms of the best performing aluminium alloy out there, it's actually quite a simple one. It contains a bit of aluminium and a bit of magnesium, and then the only other thing it contains is about 0.1 to 0.2% of scandium, which was the last of those elements I mentioned earlier.
Scandium is a metallic element I've never heard of before.
That's because it's extremely rare.
Yeah.
We only make
Where is it in the periodic table?
It is number 21.
Oh.
So it's a little bit lighter than iron.
So here's something that's really rare, but it's lower than iron.
That's right. It's one of these rare earth elements. So actually, globally, it's not as rare as all that. It's similar amount of global abundance. I've got a sheet here with the global abundance.
Yeah, I see that.
It's about the same global abundance as copper and nickel. But the problem with rare earths is that they don't tend to turn up grouped up in their own mineral. They're sort of dispersely diffused through all of the other rocks in the world. And that makes it really difficult to mine.
That's a hell of a lot of ore you've got to go through to get what you want.
Exactly. So it tends to be extracted only as what's called a companion metal. So it's extracted along with something else. And in particular, as a companion metal, when you're making a bunch of other materials which are also there often in fairly small amounts and which you usually have to have already dissolved up in an acid or something else in order to get them in solution.
Is it by any chance a companion metal of aluminium? And we normally get aluminium through bauxite, don't we?
It is.
It is?
It is.
Oh, no wonder you're homing on that one.
So in our world, in the world we live in here, scandium turns up in bauxite, and the processes we use to extract alumina from bauxite are we boil the whole thing up in sodium hydroxide, which is a pretty nasty process, bioprocess, and it does some horrible things, and it makes there's quite a nasty toxic tailings called red mud. Now, you might have heard about red mud because it's a significant environmental issue around some of the bauxite mines around the world, particularly in South America. And that's
not the stuff, it's not, what do we call it, the dreg? Is it dreg that's down there?
Dross.
Dross, that's right.
No, dross is totally different, and we can talk about that in a minute. But red mud happens overseas. Anyway, that red mud contains iron oxide and contains copper, but it also contains a bit of scandium. Now, at the moment, the world doesn't use that particular source of scandium to make scandium. We actually only make about 10 to 15 tons in the entire world of scandium at the moment. And that's because there aren't that many uses for it. And the only processes we have tend to be attached to mines that are also making other rare earths. So they're making a whole suite of these rare disperse elements at the same time.
And what happens if you mix tiny bit of scandium with aluminium?
It gets a lot stronger.
Mm-hmm.
So
and
0.2%
but
of
when
scandium.
you're smelting it, you don't need too much of a high temperature and you can bend it into all sorts of things.
That's right, absolutely. So if you put 0.2% of scandium into your aluminium... So
it's light?
It's very light. 0.2% wouldn't matter anyway, right? It's virtually none of it. So we put it in... and that increases the strength by a factor of 15 straight off the bat, with virtually that 2 parts per thousand in there. So that's, I think, probably our best modern example of what might be mithril.
The elves had their own version of mithril, I think, called Ithildin. This was the kind of mithril that they used on their buildings or whatever decorative stuff, and it glowed, but only in starlight, right?
Mm-hmm. Well, that seems to be what the book's saying. Now, there's a question about this glowing business, whether it reflects or whether it's something you can see. But that seems to be the story, is that we have this inlay of this metal that we inlay into whatever our base background is, and you can't see it in sunlight. So that's an issue, because we've just said that mithril is silvery, right? So we're going to have to do something to our silvery. But that they do have a technique where they convert this mithril into this Ithildin, which you can only see in starlight. So how do we do that? Well, actually, I think that the fact that we've picked an aluminium alloy here is quite useful, because there's a technique that you can use with aluminium which is quite widely used to protect aluminium parts today, and it's called anodization. And so this is actually pretty much the exact opposite of what you do when you win the aluminium in the first place. So when you electrolyse aluminium, you have your bauxite and your cryolite, and you stick in two big electrodes, and you run current through your bath, and all of your aluminium moves towards the cathode where you donate electrons, and it comes out as metal. Now we've got our solid aluminium, and we put it in as this thin foil into our inlay or whatever else. Or, to be honest, we've just got a big metal box that we've got a whole lot of electronics in, because that's what we do in today's society. And we want to protect that surface. What we can do is we can just hook up exactly the opposite way around, and we now, instead of having our aluminium as our cathode, we have it as our anode, and we do this at room temperature. And what happens is we now grow an oxide layer all the way back round the outside of our aluminium, and we can grow that quite thick. And it's porous.
When you say quite thick,
relatively speaking,
yes.
we're talking of tens to hundreds of microns here.
Yeah.
Tens of microns probably is a sensible number.
For somebody at the MacDiarmid Institute, that's quite thick.
Yes,
but
it is.
For us ordinary humans, it's not very much.
Well, no, it isn't. But
it's enough to do maybe what.
Well, what it does,
Ithildin does.
What it does is it forms this porous surface, and so when we anodize a surface. In industry today, what you do is you then add a dye into that porous surface, which is absorbed inside the porous nature. And so black anodized aluminium you'll find everywhere. They're black boxes. Most of the stuff in this studio, I think, is probably powder coated, but they don't look dissimilar, to be honest. And that's a very good way of protecting the surface of the aluminium anyway. It makes it a lot harder, and it gives us this surface that we can then do other things with. So the first thing we've done is we've now made it black. So that helps if we put it into
absorbing all the light, all the sunlight.
That's right. So if we now put that into our rock in face, I think in the films at one point when they go into the mines, you see the lettering come up around the top, and I think that's supposed to be Ithildin at that point as the starlight comes up. So we put it into our inlay. You can't see it in the sunlight until the sun goes down and the stars come up, and at that point it appears. So the question then is, well, what if we've made it black and it doesn't reflect anything? How can we now see it? And so there's a couple of possible ways we could do this. We could come up with some clever coating that just reflects the starlight. It takes the fact the starlight is a different colour, maybe than the sun is, and by doing
different spectrum,
different colour spectrum. That's
because each star has its own spectrum signature, doesn't it?
It does, but if we've got a lot of stars in the sky, they're all going to be mixed up, of course. So, but nonetheless, we could perhaps postulate that in Middle-earth, we've got lots of quite close stars that are quite strong, and maybe they're a bit hotter than Middle-earth stars, so they're a bit bluer.
Right.
That's quite helpful.
So for that to work, we probably have to have a Middle-earth that's not this Earth. It's a completely different Earth with a completely different set of stars around it.
Yeah, you remember that bit where I said we had dragons? Yeah, and orcs. So I think we can be reasonably clear that we're not necessarily on our Earth. But anyway, if we're returning to this postulate, if we say we've got these stars which are a bit bluer and a bit closer, that gives us something to work with, because now we've got quite a significantly different spectrum to our own sun. And so we could do one of two things. We could try and reflect that. We could try and make what are called selective reflective surfaces. So these consist of lots of thin films, which you sometimes see on the top of things like solar cells or in binoculars. And depending on how you use these, you can just reflect a single light back at you, single colour of the light back at you, or you can use it to try and avoid any reflection whatsoever. And that's a possibility, quite tricky to do. So the other way we could do this is we could perhaps look at a phenomenon known as luminescence. And so that then is a phenomenon where a material will absorb blue light, and then it will give out light at a longer wavelength. So it'll give out what light in the green to red part of the spectrum. And the way that works is the blue photons coming in have more energy than the photons coming out. So the photons come in, they excite an electron somewhere in this material, and that electron then just drops down ever so slightly, loses a tiny amount of energy, and then it goes through a transition. So one of these quantum transitions where it moves from one level in an atom to another level in the atom. And when it drops down, it gives out a photon of a certain energy. And that energy corresponds to the colour we see.
However, why would that only work with starlight?
Well, so the trick here is to find a luminescent material which is reasonable but not so bright that it swamps whatever you can see in sunlight. So if sunlight is a lot brighter than starlight, and the irises in our eyes close up, and our sensitivity to light is much lower during daytime. So we could perhaps have a luminescent material that we put enough into our inlay that when it's dark we can see the luminescence from this blue light, but when it's light, we can't actually see it because the diffuse spectral sunlight swamps everything else.
So the sunlight will create some luminescence, but it's drowned out by the sun's light.
Absolutely.
However, starlight gets the same thing, but there's not enough starlight to drown out the luminescence coming back to our vision.
That's right. And I think it's really important to remember that when we talk about how things appear, actually we have spent as much time talking about how our eyes respond to the world around us as we do about how those materials themselves do. So our eyes are amazing things. They have a massive range of sensitivity, and the ability of our irises to shut down and open up under different light conditions means that we actually end up seeing quite differently in the dark to the way we see in the light.
But Chris, do you think, is there anything around at the moment that does what you've just said?
Well, yes.
Could be done. Can you give me an example?
So white LEDs.
Yeah.
So white LEDs basically consist of a big blue light sitting behind a phosphor coating. And that phosphor coating is usually made of something called cerium YAG. So this is yttrium aluminium garnet with some cerium isolated in it. And the cerium atoms are the important bits here because they absorb and give back out the light. And the garnet then is what's called your matrix material that makes sure that the electrons, once they've been excited, don't go anywhere else but back into the cerium. And so that's exactly what that system does. Nowadays, we coat these phosphors on top of our blue LEDs, and we shine blue at them from behind, and in front it looks white because it gives out these white light.
Don't we need electricity for this, though?
Well,
even if it's a small amount, we still need electricity, don't we? It's an LED. It's a light-emitting diode.
I could take the phosphor off and I could shine any other blue light you liked on it and the same thing would happen. So the key is the blue light. So the whiteness of white LEDs is not to do with the electricity at all. It's to do with photons moving inside that LED, moving between the blueness, because you can only make an LED out of one colour, right? LEDs have a colour defined by the material you make your LED out of. So blue LEDs, which are made out of gallium nitride, were quite a big deal when they were discovered back in the 1990s and early 2000s. Until then, we only had red and green ones. And so if you look at lots of 1980s and 90s sort of technology, they're sort of typified.
No blue?
There's no blue.
But where did the blue light discos come from in the 80s then?
That is a very good question, but they weren't LEDs, were they?
They
weren't
LEDs.
I think they had colour transparencies on the front of those spots, thinking about them back when I was a kid.
Was it neon? I mean, blue. Neon does a lot of good blue,
red.
Doesn't it?
Neon's red.
Neon red?
Yeah.
What does the blue then? When you?
It's one of the other noble guesses, I'm afraid.
That's a massive tangent. Sorry about those listeners. But there is another whole side, I think, to the Mithril story in Tolkien, and that is that it was a great source of power and wealth for the dwarves, but it was also in terms of the Mines of Moria, a of trouble, because that's where they got it from, and they kept digging for it because there was demand for it, because it was so useful, it was so valuable. They dug and dug and dug, and eventually they dug up a Balrog, which was some horrible creature that then wiped them all out.
That's right. So I think that there's some fairly blatant metaphors going on in this part of the story. So I think the story goes that the dwarves dug down and they released the Balrog, which was this demon-like monster, from the depths.
That then Gandalf had to fight in Lord of the Rings.
Eventually, but
run, you fools!
Prior to that, this Balrog had done a pretty good job of shutting down mine operations.
Yeah.
So Durin's Bane runs around the mine and deals with all the dwarves, and eventually all the dwarves run away. And so no more Mithril is produced.
Durin's Bane was the Balrog, wasn't it?
That's the Balrog,
yeah.
That's right. What we find by the time of the books is that the only Mithril that's being used in Middle-earth is material that's been recycled. It's a classic circular economy, right? We've got the Mithril that's been mined over the previous thousands of years, and the elves are carefully maintaining it. They're recycling it. They're bringing it back. They're melting it down and turning it into new artifacts. But they've got this diminishing supply.
Thanks for listening to this episode of Sci-Fi Sci-Fact, hosted by me, Bryan Crump, produced by Andrew Robertson, and of course made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci-Fi Sci-Fact on the RNZ Podcasts page. RNZ Podcasts are also available on Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.